Some reactions involve gases as reactants or products. And so if we're doing stoichiometry, how do we measure the quantities of the gases? Well, we'll often measure them in terms of volume at a specific temperature and pressure. So we can use the ideal gas law to calculate moles from the volume, the temperature, and the pressure. And so we've seen this already. Moles is equal to pressure volume divided by temperature. If we need the volume, we can calculate that also using the ideal gas law. So volume would equal nRT over P. Question? No. If this is happening at STP, things become much simpler because then we can use the molar volume of a gas. A mole of gas is equal to 22.4 liters. Just a note, when we're talking about gas pressures here, they could also be partial pressures because there may be other gases in the mixture. So our general stoichiometry path was grams to moles to moles to grams. Right? Grams to moles to moles to grams. So we've always got this moles in the middle thing. But now with the gases, we may have pressure, volume, temperature of a gas to moles to pressure, volume, and temperature of a different gas. Okay? So it's variations on that grams to moles to moles to grams. So let's do an example. In the following reaction, 4.58 liters of oxygen was formed at pressure equals 745 millimeters of mercury and temperature equals 308 Kelvin. How many grams of silver oxide decomposed? So we have a chemical reaction occurring. We've got oxygen being formed, Ag2O being decomposed, so this is a stoichiometry problem. There's the balanced chemical equation. I'm going to write the information that I have under the corresponding formula. So it's giving me information about oxygen. So it's telling me I've got this volume, 4.58 liters. The pressure is 745 millimeters of mercury. And we know where that's going, right? We got to convert that. Let's just do it now. Anybody wondering why we don't just measure things in atmospheres? Why do we have to do all this converting? Well, atmosphere is a very large unit, and so we end up with all these decimal places. So we just typically measure things in millimeters of mercury or torr instead. So 0.98026. There's the pressure in atmospheres. And then the temperature is 308 Kelvin. So that was nice. They gave it to us in Kelvin. The question mark, is how many grams of Ag2O decomposed to make this much oxygen? So the path here, we've got the moles in the middle, moles of oxygen to moles of Ag2O to grams of Ag2O. In the first thing, what we've got is we have a pressure, a volume, and a temperature for the O2. So we're going to convert that into moles, and then we can go to moles of the other and grams. This first step involves using the ideal gas law. So we want to find out how many moles. And so there we go again with the N equals PV over RT. So we've got our pressure and our volume. Divided by, there's R again. We probably are all getting that memorized just by sheer repetition. 0.08206 liter atmospheres per mole Kelvin. and then dividing by the temperature, 308. Zero 0.17763. That's the moles of oxygen that were produced. So now we're here, moles of oxygen. So we can go to moles of silver oxide and grams of silver oxide. So moles of Ag2O divided by moles of O2. What's the relationship? It's 2 to 1. So we've got 2 moles of silver oxide forming 1 mole of oxygen. Coefficients in the balanced chemical equation. And then we need the molar mass of Ag2O. 107.9 for silver times 2 plus 16 for the oxygen, 231.8. I'm getting 82.349 grams, 82.3 grams of Ag2O decomposed. Any questions? Of course, the real question is why would you need to know that, but I can't answer that one. It's because the book is asking us. You have to tell them. Let's do an example using molar volume. And you'll see how much easier this is. So how many liters of oxygen, and there are that blessed letters, at STP. When you see at STP, you should think, hey, I can maybe use 22.4. Are required to form 10.5 grams of water. So there's only one number in here, the 10.5. So 10.5 grams of water. And the question is, how many liters of oxygen? So question mark liters at STP. So the path is going to be grams of water to moles of water to moles of oxygen to liters of oxygen. Because it's STP, for this conversion, we can use 22.4 liters per mole. So we'll start out with our 10.5 grams of water, and we're going to convert that to moles of water. So 1 mole of water weighs 18.02 grams. And then we're going to have moles of oxygen divided by moles of water. We look at the balanced chemical equation, and we get 2 moles of water for every 1 mole of oxygen. Then here I want liters of oxygen on top and moles on the bottom. It's the volume of 1 mole. So 22.4 liters is 1 mole. So 10.5 divided by 18.02 divided by 2 times 22.4 equals. So 6.53 liters of oxygen. Any questions? Now, if you forgot 22.4, you could use standard temperature and pressure and the ideal gas law, and you could calculate from moles of oxygen how many liters there are.